Many processes are reversible, and for example the vaporization and condensation of water, where we have a sealed container and water molecules escape due to vapor pressure, and at the same time some molecules condense. An equilibrium is reached when the rate of evaporation is equal to the rate of condensation. And another example is a sparingly soluble salt. So silver chloride is not normally soluble because it's a halide of silver. But if you add excess silver chloride to water, then the solid dissolves, and at the same time the ions combine to produce an equal amount of solid. An equilibrium is reached when the rate of dissolution is equal to the rate of precipitation, and no further changes can be observed. And you get a diluted solution of ions in equilibrium with undissolved silver chloride. So the main point is that when equilibrium is reached, the reactants and products are both present, and the molar concentrations or partial pressures of all species remain constant. And the equilibrium state is dynamic, meaning that the forward and reverse processes continue to occur at equal rates. So the processes don't stop occurring, they just keep going back and forth at equal rates. And this results in no net change that can be observed at the equilibrium state. We can use graphs of concentration, partial pressure, or rate of reaction versus time to understand when chemical equilibrium is established for simple chemical reactions. So here we have the Haber process, which represents the industrial production of ammonia from nitrogen and hydrogen gas. So for every mole of nitrogen that's consumed, 3 moles of hydrogen are consumed, and 2 moles of ammonia are produced. So before equilibrium is established, there's a change in concentration of the reactants and products, and when equilibrium is established, the concentrations remain constant. And here we can observe from the rate of reaction versus time, before equilibrium, the rate of the forward reaction and the backward reaction is not equal, but when equilibrium is established, the rate of the forward and reverse reactions are equal. So while the concentrations are constant, they're not necessarily the same. And the forward and backward reactions still continue to occur at the same rate.